Every single day, a venomous snake swallows prey that's already full of its own venom. The exact same toxin that can stop a human heart or shut down a nervous system in minutes. It goes straight into the snake's stomach, gets digested, and nothing happens. No symptoms, no collapse. Business as usual. So here's the actual question people almost never think to ask. If a snake carries one of the deadliest substances on the planet in its own mouth every single day for its entire life, why doesn't it ever kill itself by accident? The first part of the answer is honestly kind of anticlimactic. Venom, chemically, is mostly just protein, the same basic building blocks as the meat on your dinner plate. When a snake swallows envenomated prey, that venom hits stomach acid and digestive enzymes exactly like any other protein would and gets broken down into harmless amino acids before it can do anything dangerous. Eating venom and getting injected with venom are two completely different problems. Digestion neutralizes it almost immediately. Injection. Venom bypassing the gut and going straight into tissue or bloodstream is what actually matters, and it's a much more dangerous delivery method than swallowing could ever be. So the real question isn't about eating. It's about what happens if venom gets directly into a snake's own bloodstream through an accidental bite, a scuffle with another snake, or venom leaking somewhere it shouldn't. And it turns out, snakes have stacked up several separate, independent defenses against exactly that scenario. Not just one clever trick, but a whole layered system. The first layer is mostly mechanical. Venom is manufactured and stored in dedicated glands positioned behind the eyes, connected by ducts to hollow or grooved fangs built to inject outward, away from the snake's own tissue. There's muscular control involved in exactly when and how much venom gets released with each bite. Snakes can actually choose to deliver a dry bite with little or no venom at all, conserving it for situations where it's actually needed. Fang sheaths help keep venom contained until the precise moment of a strike, rather than constantly leaking into the snake's own mouth tissue. It's less immunity and more basic plumbing. An entire delivery system engineered to point in one direction only, with safeguards built in at every stage before the venom ever reaches a target. Even spitting cobras, which can accurately spray venom several feet toward a threat's eyes, have specialized musculature that redirects pressure through modified fang channels specifically to launch venom outward, without any of it pooling back into their own mouths in the process. The second layer of defense is biological, and this is where it gets genuinely interesting. Snakes carry antibodies in their bloodstream that specifically target their own venom, essentially a built-in, partial antivenom running through their veins at all times, similar in concept to how antivenom for human snakebite treatment is actually produced. Researchers inject small, controlled doses of venom into horses or sheep, and those animals' immune systems build up antibodies against it over time, which then get harvested and purified into the antivenom used in hospitals. A venomous snake's own body appears to run a slower, lifelong version of that exact same process, using itself as the source. Some species have gone even further and evolved modified cellular receptors. The same receptor sites venom neurotoxins are designed to latch onto in prey animals, altered just enough at the molecular level that the toxin can't bind properly anymore. If the lock doesn't fit the key, the neurotoxin has nowhere to attach and simply passes through harmlessly, unable to trigger the paralysis or organ failure it would normally cause. Researchers studying this phenomenon have compared it to a slow-building tolerance, not unlike how repeated small exposures can build resistance in other biological systems. Since a snake's own venom is essentially always present in trace amounts near its salivary glands and the surrounding tissue, its body ends up chronically exposed to minuscule quantities over its entire lifetime, and gradually builds up defenses against the exact toxin it produces, almost by proximity alone. And this is the part that makes the question actually interesting instead of a flat, boring no. None of this adds up to true, absolute immunity. It's resistance, built in layers, and resistance has limits. There are documented, confirmed cases of snakes dying from self-envenomation. One well-known case involves the brown tree snake, where venom ended up directly in the animal's own bloodstream rather than being safely contained by the usual mechanical and immunological defenses, and it proved fatal. Researchers who study rattlesnakes have run blood serum tests and found measurable, but distinctly incomplete, resistance to their own venom. Enough to shrug off minor exposure or a small accidental scratch, but not necessarily enough to survive a full, concentrated dose delivered straight into a vein the way it would be during an actual predatory strike. There's also a messier, Far less dramatic way self-bites can turn deadly, and it has nothing to do with the venom's toxicity at all. In several recorded incidents, a snake that accidentally bit itself. Often while striking clumsily at prey and missing, catching its own tail or body instead, died afterward. But when researchers investigated, the actual cause of death was tissue necrosis and secondary infection from the physical puncture wound itself, not any chemical effect from the venom. So even a headline like "Snake dies from biting itself" doesn't always mean the poison did the killing. Sometimes it's just a bad, dirty wound that never had a chance to heal properly. Now here's where things get even stranger, because self-envenomation was never really the biggest risk in a venomous snake's life. Other snakes are. When male snakes of the same species compete for territory or access to mates, you might reasonably expect a venomous showdown. It almost never happens that way. Most species settle these disputes through ritual combat instead. Two males rearing up, intertwining their bodies, and wrestling to physically pin or overpower one another, specifically avoiding venomous bites entirely throughout the entire contest. It's less duel to the death and more an elaborate, full-body arm wrestling match that can go on for quite a while before one snake finally concedes and slithers off. But according to venom researchers who've studied this, if two snakes of the same species did seriously bite each other, the resistance built up over a lifetime of low-level self-exposure would likely be enough for both animals to survive the encounter. Cross the species line, though, and the odds get dramatically worse. One toxinologist studying rattlesnake venom put it bluntly: the more distantly related two snake species are, the more likely their venoms are to be genuinely, mutually lethal to each other, because neither one has built up any resistance whatsoever to a toxin cocktail its own body never evolved to deal with. A rattlesnake and a cobra, bitten by each other with no prior exposure to build any tolerance, would very likely both die. There's a reason nobody's run that particular experiment on purpose. And that same distinction, same species versus distantly related species, actually explains one of the single most impressive examples of venom resistance in the entire animal kingdom. Kingsnakes are born, not trained, with a resistance to pit viper venom, the venom of rattlesnakes and cottonmouths, so strong that it functions as effective, near total immunity. This isn't something they build up gradually through repeated exposure the way a snake develops resistance to its own venom. It's baked directly into their genetics from birth, inherited from countless generations of ancestors that specialized in hunting and eating venomous snakes, and needed that resistance simply to survive doing it. That genetic inheritance is precisely how a kingsnake can grab, constrict, and calmly swallow a live, fully venomous rattlesnake without a second thought, completely unbothered by repeated defensive bites during the struggle. King cobras take this concept even further, regularly hunting and eating other venomous snake species as the primary component of their entire diet, which means their bodies are constantly dealing with a whole range of different toxins, not just a single familiar one they produce themselves. It's a level of accumulated biochemical toughness that makes their own venom look almost secondary by comparison. Just one more toxin among many their system has learned to shrug off. So, can a snake actually be killed by its own venom? The honest, slightly unsatisfying answer is, technically yes, but it's genuinely rare. And more often than not, it isn't really the venom's fault. A venomous snake's body is remarkably well defended against its own toxin on multiple independent fronts. Mechanically, through fang design and controlled delivery; immunologically, through circulating antibodies and modified receptors; and evolutionarily, through generations of chronic low-level self-exposure. Confirmed cases of true self-envenomation death do exist, but they're the rare exception, usually involving venom reaching the bloodstream through some unusual pathway that manages to bypass every one of those built-in defenses all at once. The far more dangerous threat to a venomous snake was never really its own fangs, or even a close relative's. It's every other, more distantly related snake sharing the same territory. Carrying a toxin its body has simply never had a reason, or an evolutionary chance, to prepare for.